Hi everyone, welcome to this session. I'm Valentina Rossi, marketing specialist for Zapi Group. Please remember that this session is also being recorded and it will be available to watch on demand following this session. If you have any questions during the session, please add them to the question and answer. You can find that tab to the right of your screen. Note that your question will be sent privately. With that, I would like to introduce our speaker, Gareth Jones, Managing Director at Zapi Group UK, who will be speaking today on the system level consideration and challenges in a transition to electric. Hello, everybody.
Okay. Thank you very much, Valentina, and hello, everybody, and welcome to the presentation on system level considerations and challenges into a transition to electric. So as Valentina introduced, my name is Gareth Jones, and I work for Zapi for nearly 20 years now. And for about 10 of those years, a bit more than 10 of those years, I've been working on electrification projects. So I have quite a good experience in this topic. So first of all, just to prepare you with the agenda for the presentation today, I'll start with a brief introduction. And then I've split the topics into technical considerations and some other considerations. The main focus of the presentation will be around the technical considerations because I'm an engineer, so this is always where my focus is. But after the technical, the technical considerations, we will look at commercial, service, legislative considerations, market considerations, commercial viability, and support options. All of these topics need to be carefully considered really before you start an electrification project to really ensure that you're making the right move and that you'll be successful at the end of the project. Okay, so I'll move on. So first of all, an introductory slide. If you're thinking of electrifying your ICE machine, you'll have many questions. Where do you start? Today, we will run through at a high level the main considerations that will need to be evaluated before deciding to proceed with an electrification project. So many OEMs may feel apprehensive about such a project due to resource constraints and or lack of know-how with electrification. So the main focus of this presentation will be from the perspective of an OEM, which may have the telematics data, which can help at the start, or maybe is lacking the capability with modeling and other tools. So we look at it from that perspective. So that can be small OEMs, but also very large OEMs who are really new to the electrification journey. So first we start with the technical aspects. So just to highlight again, because there are so many considerations and challenges which you need to think about, we only have time to briefly touch on each of these topics. We could talk for hours on each of them individually, but this is really focused at companies who are thinking about starting the journey towards electrification and what are the headline topics which they will definitely need to consider. So first of all, the starting point will be the performance and duty specification. So talking about performance, many OEMs do not have a clear idea about the real power and torque requirements for their application. They've just always relied on the fact that the engine does the job and they don't worry about it. So a good starting point is to calculate the actual real power that you need to achieve the application requirements. So don't just consider the IC engine power, because this the IC engine will work in a different way compared to the electric motors, which you'll need to be considering. One second. Okay, so the so you have different functions which you will need to think about. Usually there's a traction function, and for the evaluation and calculation of your traction power, you'll need to think about the vehicle speed, the weight, the load, the gradient, the gear ratio, and the wheel diameter. So from these, you can calculate the power that you need to achieve your traction demands. Also, there will usually be hydraulic functions. And from these, again, you need to work out the power. But for hydraulic functions, you will need to know about the pressure, the flow rate, and the pump CC, so that you can work out the power requirements for your hydraulic functions. Usually as well, there will be some auxiliary functions. And of course, you need to add the power requirements for these into the overall picture. But of course, there can be many different auxiliary functions. So you really need to know the details of each individual auxiliary function. So once you have these functions defined and you understand how you're going to calculate these, you'll need to decide on some reference working points to define. So for example, you might have specific speeds with specific loads going up specific grades. So you can brainstorm and work out which these reference working points are going to be, and that will give you the power points for specific aspects of your application requirements. So after you've done this task, you know how much power each function will need. Then you need to move on to the duty cycle. So that's trying to figure out how long you need the power for each of these reference points. So usually an understanding of the duty cycle is very hard to get, especially when there's no telematics data. And usually every application has a very unknown and variable customer use case. And because of this, everybody tends towards the worst case scenario. And the problem with tending towards the worst case scenario is you end up with an overestimation of your energy requirements because you've overestimated the duty cycle. So the result for this can be you overspecify the battery, which can mean the battery is more expensive than the application can afford. Okay, moving on. So that leads us on to the energy storage that is required to meet the specification. So from the performance spec, you know how much power you need, and from the duty cycle, you know how much time you need the power for. So together, this tells you how much energy you need. How are you going to store the energy? So there are many different options, but the two main choices which we see regularly are lead-based or lithium-based batteries. So some pros and cons of the two. So lead are heavier, they are bigger, they are slower to charge, they have lower efficiency and shorter life, but they have no battery management system required and they are less expensive. So lithium batteries, on the other hand, they are lighter, smaller, they have higher efficiency, longer life, faster charge, but they need a battery management system and they are more expensive. This may lead people to think, why use a lead acid battery at all, or a lead type battery at all? And of course, there's a few reasons for that. One is lead acid has been around a long time, whereas lithium is relatively new. Also, the cost of the lead acid or the lead type battery is still much cheaper than the lithium type of batteries. And also in some applications, the weight of the lead is an advantage. For example, material handling applications and access work platform applications, they really appreciate the extra weight of the lead because they can use it for ballast to give stability to the vehicle. Over on the right of the slide, you can see some quantifiable ballpark information about the comparison between the two battery types, just to give an idea of the kind of magnitude of the difference between the two types. So you can see a huge improvement in the cycle life of lithium batteries compared with lead acid. Sometimes even greater than that can be seen. Efficiency, you see a big improvement. The weight size, a big improvement with the lithium, but of course, on the other hand, the cost is much in favor of the lead acid. Okay. So another topic which is always at the forefront of discussions when someone is developing a new electric vehicle or moving to a new electric vehicle, what is the right voltage level for their application? Everybody has to think about this. So I split it into high voltage and low voltage here for a couple of comparisons. And for us, what we call high voltage is above about 140 volts DC, and what we call low voltage is obviously below that. And that transition point in our industries comes about because of the technology used in the motor controllers, the power switching components which are used in the low voltage controllers is only good up to around 140 volts DC. And then we have to move to a new technology, for example, IGBT technology, to switch the higher voltages at a good price. So what are the pros and cons of the high voltage and low voltage solution? So for high voltage, you get lower current, which is a benefit. You can get higher power, but on the downside, there are more safety concerns, obviously because of the higher voltage, and generally you get a higher systems cost because of the extra safety aspects you need to implement to protect people from the higher voltages. So inversely, with the lower voltage, there are less safety concerns, less system cost, but you can get lower power, and you need higher current. The negative aspect about the higher current can be around the fact you need bigger conductors, and transport in this higher current through connectors is more of a challenge. And also there are generally more losses in the high current vehicles through the conductors. I²R losses are higher. Other things which you would need to think about is the availability of the components. So for example, 48 volt components, 48 volt DC components are very readily available from the material handling market. So it could make sense that you use these mass-produced components for your application. Use that 48 volt level. Or it could be that you're more thinking along the lines of the 350 or 400 volt application. They could have a very high availability of components from the automotive market, which could fit nicely into your application. Of course, another important thing is regulations around the voltage level, which there are a lot of. A lot of people try to stay below 60 volts because of the automotive regulations related to that. Another thing is about the service skills. So it's easier to set up your service department and network to service lower voltage application, low voltage equipment, rather than high voltage equipment. The servicing of low voltage electric vehicles is well established and well known from applications in industries like the material handling industry. What I always say is, in general, use the lowest voltage that makes sense for your application. That's a rule of thumb which I always recommend. And on the right-hand side, you can see a table which can give you some comparisons of voltage levels and power levels. This is a very grey definition, and for sure there's a lot of changeover between the different voltage levels. But this is a guide which kind of makes sense. So next, a very important aspect to think about is charging. So charging is a very important consideration which needs to be carefully evaluated. One of the biggest drawbacks for electric vehicles is the challenge of replenishing the energy in a convenient way for the end user where they need to replenish the energy. So it's not as easy as filling up an IC vehicle with fuel. Charging is, the big drawback for electric vehicles. So there are many considerations, and I've listed a few of here which you need to think about, because so thinking about the charging is something you should do right at the start of the project, not at the end, because believe it or not, this has happened. I've been involved with projects where the charging infrastructure has not been considered at the start. They've waited till the end, and then they've had to scratch their heads while they figure out how they're going to charge the vehicle. So very important to think about this at the start of the project. So some considerations that I've listed here are, importantly, first of all, will there be mains AC power to the machine? Of course, that's important. And where will it be available? So next, what voltage and power will be available from the supply? Will you have three-phase? Will you have single-phase? Which regions will your machine be used in? Because different regions have different voltage levels They have different connectors and therefore different power limits which you can draw from the mains grid. You need to keep all of this in mind. And then you need to ask yourself, will you be using opportunity or fast charging? Will you be using onboard or offboard or a combination of both? Will you have to use swappable batteries? Will you be able to charge overnight? Can you use mobile power banks? There's other considerations as well with charging, but just to highlight that it's something you need to think of carefully. Okay, so another topic which is very frequently discussed during a project is what kind of motor type will fit best into the application. So there's considerations which will always need to be thought about. And the main one is really the power and torque density. So how much space is there for you to fit the electric motor into? If you are replacing a hydraulic motor, for example, perhaps there's not much space in there at all. So that could probably drive the decision of what motor type to use. Another important aspect is, of course, always the cost. That works into every evaluation of what product to use. And so with motor types as well, there's not one motor type which fits all applications. For different motors, they have different characteristics, which mean that different working points suit better specific motors. So for example, one motor type might be good for a low-speed pump application, but not good for a high-speed traction application. So you have to pay attention to where you will be using the motor to find out where you need your sweet spot for the efficiency to be. Another important thing to think about is the availability and the maturity of the technology. Maybe you want something which is tried and tested out in the field for many years, rather than a new motor technology which has got less miles on the clock from the point of view of reliability in the field. So that's something to think about. So I've just listed 3 motor types. There are many other motor types, but these are the 3 motor types which I wanted to highlight because these are the ones which we see and use mostly at the moment, I would say. So AC induction, really the workhorse of industry, and just some comparative type motor types. So AC induction motors give the best availability. They have good price. They are easy to control, because the controller companies have a long experience of managing these type of motors. We have no back EMF issues, which is an important factor when you want to go at high speed. But the downside for the AC induction motor compared with some of the other motor technologies is they have poorer power density, relatively lower efficiency. But all that being said, they are still good for high-speed applications, and they are very flexible motor. Induction motors can do all of the activity, all of the different applications can be driven from an induction motor, which is why they become so prevalent over the past years. So now, next I mentioned IPM motor. This is a type of permanent magnet motor, which we are seeing more and more of. And so the availability of this type of motor technology is improving all the time. So we can get good prices with these motors, particularly if you use ferrite magnets. They are more challenging to control compared with induction motors. But that being said, most motor controllers now have no problem with controlling these kind of motors either. There's enough experience being gained, I would say. So these motors do have back EMF issues. That is due to the permanent magnet material inside them. And they have, relative to induction motors, good power density and good efficiency. As I mentioned, they have they are good for applications for low speeds, particularly good for low speed applications like pump applications. But for high speed applications, because of the permanent magnet material and the back EMF, sometimes you will need to evaluate over voltage protection in the motor controller. So the last on the list is the SRPM. That's the synchronous reluctance permanent magnet motor. These are really the the least available of the three that I've mentioned. They are more challenging to control because they are generally newer to the market compared to the other two. They have less back EMF issues compared with the IPM motor because they have less magnet material inside them. They have good power density and good efficiency, and these are good for high-speed applications because of that characteristic of less back EMF. Okay, so IP ratings. This always comes up in conversation, particularly around motors, and it needs to think about, and everyone always talks about this. We've had many conversations about which is the best IP rating for any particular application, and really there's no right or wrong. In each case, you need to consider and evaluate and find out which is best for your application. So some general comments and considerations. The higher the IP rating, the higher the cost in general. The higher the IP rating, the more chance of thermal issues. This is because the more you enclose the motor to protect it from the environment, the more you make it difficult for the heat to escape. Simple as that. Because all of the components generate heat, so and you need to dissipate that heat. So higher IP rating can make that more challenging. And another point is that higher IP rating isn't necessarily better. I'll use the example of IP66 versus IP67. They're not incrementally better compared to each other. So, for example, IP66 gives good protection against jets of water, whereas IP67 gives good protection against submersion underwater. Perhaps you need protection against jets of water, in which case IP66 is better for you compared with IP67. I mentioned again availability of the parts. In general, you'll want to use things which are readily available and off the shelf. And if there's an IP65 component which is readily available and off the shelf, maybe you can use that and use some other method to protect it in order to make it suitable for your application. Important to keep in mind as well, IP ratings may not remain valid after a long time in the field. There's a lot of environmental impact which some things are exposed to, for example, physical damage and sun and weather. So over time, particularly plastic components, this IP rating may start to degrade. So you can't really rely on the IP rating, which is given on a new component in a lab condition. You need to think, what will the IP rating be after it's been knocked about in the field for a couple of years? So in which case, again, maybe some extra protection will be required. And just a last comment there. Sometimes it is more cost effective and better for the application to use a lower IP rating, but use other means to protect the component. So maybe, as an example, maybe an IP20 motor can give you a more power dense motor for your application, and you can protect that motor by using some kind of shield. So you've got a better, you might have a better cost point, you might have a better performance, and you might be able to use some other method to give you the protection from the environment, which will do the job. So applicable regulations, so often a bit of a grey area. So particularly in new markets which are newly adopting electrification. So usually application-specific regulations don't yet exist, and people will be uncertain about which regulation to use and what they need to do to make sure they're proceeding in a professional way with due diligence on the regulations. So what considerations do you need to think about regarding the regulations? So EMC and EMI, very important. Another very important thing to think about at the start of the project is the EMC and the EMI. If you wait till the end and then try to, without even evaluate in this aspect and then try to pass your test, maybe you need to redo a lot of work. So the voltage levels, as we spoke about before, strongly linked to specific regulations. Functional safety, very important. And you need to think about, are you going to be using this for domestic use or industrial use, on highway, off highway? And these considerations will help guide you towards some potentially useful reference regulations. I've mentioned a couple of examples of things, but there are many to find in order to help guide you along the way. So EN 13849, safety of machinery, very important general regulation, and from which gives a lot of guidance on a lot of the topics mentioned above, and is used as the basis for many of our application-specific regulations which we follow with electric vehicles. The low voltage directive may be more suitable for static machinery, but again gives useful information about how to develop safely electric vehicles. And for the on-highway or more mobile equipment, R100 and R10 give very good safety and EMC requirements for electric road vehicles. So a lot of people use that as a baseline for their safety development of their machine. So, and just to comment on there, a lot of people try to stay below the 60 volt DC or 30 volt AC, which is defined in the R100. And this means if you're following that standard, it means by staying below those voltages, you can really minimize the impact of the extra costs which need to be added to make the electric system safe and meet the standards. Which is why a lot of applications like to stay at the 48 volt or perhaps maybe 50 volts if it's a lithium battery. But this means that overall the system voltage, even when fully charged, can remain below the limits of this standard. So an important thing to think about as well with another important thing to think about with new applications is the new features which potentially you can add. So you don't need to just think of making a carbon copy replacement for your existing machine. You will be adding new capabilities with new technology, a lot more processing power onto the vehicle. So why not have a think about how you can use this to improve the customer experience? You will always get the obvious improvements from lower noise, no emissions, and improved responsiveness from the electric motors. But further than that, what new features could you implement? And this is a really important way to add some value to the new electric machine, which will probably cost more than the previous machine. So this can be an important value add for the customer and end user. So some examples could be use the readily available data to offer a high-tech HMI. Everybody loves a fancy HMI on their machine, and moving to electrification can really be give you a good excuse to implement this onto your new machine. Another factor can be easier implementation of automation. So electrification and automation really go hand in hand for sure, and automation is definitely going to be growing exponentially in the future. In most applications, you can say we'll have some degree of automation moving forward. So electrification really allows you to realize the automation of your vehicle in an easier way. Another improvement you can get is the data login. So because we have all this data, it's usually all firing around the machine, shared on the CAN bus network from all of the different controls. So data is there, and it can really be valuable for the service and warranty to have this data so that you can then use this data for warranty and service issues, but also for product improvement. and just generally, again, improving the customer experience. Again, with the electric system, the integration of electric sensors and actuators in general should be easier, and at least more possible as well. If in case on your previous machine you don't have much of an electric system, you will definitely be able to, in a more easier way, implement and integrate these sensors and actuators, which may be again able to allow you to improve the customer experience. Okay, I'm just waiting for the screen to catch up. So next we move on to the, so that's the main technical aspects evaluated. So everybody will definitely need to think about all of those points. There are other points as well, but they're just the main ones which we come up against time and time again. And if, like me, being an engineer, that's where your focus tends to be, you might lose sight of the other important aspects which need to be evaluated before you really commit to embarking on an electrification project. Because you might have a great technical proposition, but if everything else isn't aligned, then maybe the project will be unsuccessful. So I've just highlighted a few points here which we'll very quickly touch upon. So first of all, commercial, of course, very, very important, particularly because almost always, well, probably always, your electrical machine will have a higher upfront cost compared with the ICE equivalent, usually because of the battery being the main contributor to that. So will the customers in your market accept this price? So there are some things you can think about to try to mitigate this cost price increase. For example, the total cost of ownership, saving in fuel costs and maintenance costs can help tip the balance in the favor. Because in general as well, thinking about the electric vehicles have much less maintenance requirements compared with ICE vehicles. So that's something to really highlight and to try to get some leverage from. Another thing which you can use to push the OEM or customers to move to the electric version is the extra performance and features which they can realize on these machines. Again, this is a value add which can help offset the higher upfront cost. Both, these things again are linked to improving the customer experience, and you can do that with the improve the customer experience from the extra features, or indeed the things like the extra data login and the warranty fine tuning which you can get from that extra data. So other aspect which is very important is government incentives. So government incentives can be that sweetener which can help offset the higher upfront cost, and we see this a lot in many markets. And it's governments are really using this to try to kickstart electrification. So can be very useful and very important. Another thing to think about in a similar way is that you could be seeing future challenges from legislation. So this could really force the issue, force the decision, I would say, because if in the future we have legislations which really limit the amount of internal combustion machines which can be used in a specific application or a specific area, then these challenges can really make the electric the only option. So it kind of future-proofs your product. So another thing is the service network. So time and time again, we see resistance from networks to really use the new electric variants of the vehicles, and this can be because they're not comfortable with the technology. So it's very important for OEMs to really dedicate time and effort to train their service network and dealer network so that they are comfortable with the electric product, so that they are willing and proactive in selling it because they are comfortable with being able to support it. So important thing not to overlook. And again, another comment on legislation. There's more and more of a push all around the world from governments as each government is trying to drive towards their own targets around zero. So yeah, this is really going to force the hand of many OEMs to move to electric. So market considerations. So yeah, timing can be a very important consideration in your market. You may be uncertain about the readiness or the real demand from your customer base. And as we have seen already today, there are multiple factors which need to be aligned before your market will fully accept the new technology. So you could be a bit wary and uncertain about when you need to move in this direction. But in general, if you're thinking that way, for sure, I guess you realize that at some point you need to make the move. So my idea or suggestion would be don't wait too long and get prepared perhaps before your market hits a tipping point. Because development of an electric machine or vehicle may take several years before it's mature enough that you are confident and comfortable to set this free in your marketplace. So the more work you can do before you get to the mass release, the better for your confidence when you come to the point where you'll have to release it. So a slide on the commercial viability. So I've used a circular graphic to show this can be a kind of iterative process. And usually when we're talking about the cost, commercial viability, it's around the cost of the battery. So as we went through the technical specs before, you see the same sequence here. You start with your performance spec, you get your duty cycle specification, you know what energy requirement you need, you know then what system and battery cost you need. Can you use an intelligent charging strategy to reduce this system cost? And then what do you end up with? Do you end up with a product which your market will accept from a price point of view? If not, maybe you need to make some compromise on the performance spec or the duty cycle for your electric vehicle. And you can go around this iterative process until you find an acceptable price point for your market. So support options. So depending on your organization's specific competencies, you may want to find a development partner for this. There are a couple of examples here. A systems design proposal can be made by a system integrator or system supplier. To be outsourced or co-developed with a partner. These activities can really help you make the first steps along the road towards electrification, and getting somebody to help you with this activity who's got a lot of experience in this activity can really help you avoid some of the pitfalls from some of the topics we've already talked about today. So at Zapi Group, we are very familiar with going on this journey hand in hand with our customers, and we like to share the experience which we have gained in order to make it a kind of smooth process. Okay, so thank you for listening, and in case of any questions and answers, we will move over.
Yes, we have something. So the first question is, how do we determine battery capacity for a vehicle?
So we would evaluate the battery capacity. As I mentioned, we can really measure the power and the duty cycle. And from this data, which we gather from that, we can measure exactly the energy which is required for each application. The best way to really be sure of this is by using a prototype machine with some data logging componentry on there to measure everything exactly. So you can do modeling beforehand, or you can do some calculations using other methods, but really until you've seen a concept machine, that's really when you have a solid idea about the capacity of the battery that you'll need.
Okay, and the risk associated with a lithium chemistry, and how are these mitigated, basically?
Okay, so lithium-ion batteries, of course, we hear a lot about the risks related to those batteries. Particularly, we see on the news about fires and things like this. But what we do in order to mitigate that is they have a battery management system on the battery, which monitors the battery very carefully to ensure that any high temperature, for example, will be noticed, and the battery then will stop being used. So the assembly of the battery needs to be done by people who know what they're doing. And an important aspect of that is making sure that if there is a problem with one cell, this, for example, a fire, it into other cells. So using a reputable and experienced battery supplier is really important to make sure that you avoid the risks related to the lithium batteries.
Okay, and what are the solutions to mitigate back EMF issue with PM motors at high speed? Is the last one, I think.
Yeah, so the back EMF at high speed. So the problem with this, what happens when you have this problem is the motor can then generate, and it can generate a high voltage, which can damage the components which are connected onto your DC bus. So in order to protect against this, the best way is to use an overvoltage protection in the controller or the inverter. So this means that if we have a high voltage situation, we have a hardware circuit which will automatically protect the system from this high voltage which is being generated from the motor. There are other ways to get around it as well, using just making sure that you're by monitoring and looking from the design point of view at the early stage to make sure that the speed that you're going and the voltage which will be generated is safe. So you can do it from that point of view, but if you can't do that, then you need this over voltage protection.
Okay, so thank you, Gareth, for sharing your knowledge with us, and thank you for attending this session. So please join the next session from the lobby, and thank you, all of you.
Okay, thank you all. Thank you, Valentina.